So I want to present you this work that we call the side journey to Titan. Side journey because side channel attacks. And Titan, it's the name of the Google product that we worked on. And it's a joint work with Thomas, my associate at Ninja Lab, Camille Muchler, who is a PhD student at Ninja Lab and at the University of Montpellier, and Laurent Imbert, who is a CNRS researcher at the Lyon, which is a laboratory of the University of Montpellier and CNRS and a bit of INRIA people, I think. So yes. So it was a huge work, so it's a bit dense. So feel free to stop me. I think we have time, at least 1 hour, something like that. So feel free to stop me during my presentation if you want some details. Yeah. So how we began this work? It was at the conference CHES 2018, which is like the biggest conference about hardware cryptography and embedded system security. And that year it was happening in Amsterdam. And one of the keynotes was given by Elie Bernstein, who is a French guy and who is the Google anti-abuse research team leader. And he does a lot of things in cryptology. And his talk was about deep learning, how deep learning will revolutionize side channel attacks and blah, blah. And at the end of his talk, he made some promotion about the new flagship Google security product, the Google Titan security key. And Elie even offered some sample to the attendees. So he did that in the US way because he's based in California. So he was like kind of throwing some boxes of the product to the researchers that we are in the big room, in the big conference room. And so we managed to get some sample and to say, okay, interesting. Let's see. It's like side channels, the new Google security product, blah blah. Let's check what we can do with that. So what is this product? So it's a hardware FIDO U2F token. So it's a hardware token that has to be used as a two-factor authentication for login to your Google account, for instance, and for any other application or web service that supports the FIDO protocol. So now we have Facebook, Dropbox, GitHub, a lot of web services. If you don't trust only the login password way to connect to your account, you can add a second factor. And so it could be via SMS, via email. It's a bit, it adds a layer of security, but it's not so perfect. You have also mobile apps. And the best is to have a hardware token that you have to enter your login, your password, and to plug the token either via USB. But some of they have two versions of the Titan key, and some versions have NFC and Bluetooth interfaces. So you can also use like this one. You can just put it close to your smartphone and log to your Google account without connecting something. So few words about the FIDO protocol. So when we made this work, it was still the FIDO 1 version, the first version of the FIDO protocol. Now there is the second version, so there have been some improvements that I don't talk about, but the concept is the same. So the FIDO, it's an open standard for two-factor authentication. Now there is a FIDO Alliance, kind of foundation managing all the partners, but historically it has been developed by Google, Ubico, and NXP. And the idea is like for every application supporting the FIDO protocol. So yeah, that's what I said before. When you have a basic authentication based on the login password, it can be stolen by phishing attack, for instance. So the idea is to add a layer of second layer authentication for every time you connect to your account. So it's based on public key cryptography. In the first version of the FIDO protocol, it was based on ECDSA signature, so elliptic curves cryptography. Based on the NIST P256 curve for the specialist of crypto. So it's an elliptic curve which has been standardized by the NIST, the American Institute for Standard and Technologies. And the protocol works in 2 steps. It's kind of simple. the first time you want to say to your Google account, let's say that you want to add this layer of authentication, you have to register your token. So basically, what will happen is like your token will generate a pair of elliptic curve keys. One private key which will stay inside the token for the lifetime of the key, and one public key which will be sent back to the server, to the Google server, and then the authentication phase, which is performed every time you connect to your Google account. So from that, we can imagine a first side channel attack scenario. So the idea is like you have the user, he has this token, and you have the adversary. And the idea is like if you are able to steal the token during some hours, for instance, let's say you are in a conference and you let your backpack at your hotel and you go for a good dinner and some beers in a bar after that. So there is a time frame where the adversary can go to your hotel room, steal your token, try to perform some hardware attack on it, and then give it back to you silently in your hotel room. And if you succeed to extract the crypto key, the ECDSA private key, then basically you can create a clone of the token. So first we began with the teardown of the product. So first surprise was to check that actually it's FIDO, which is a Chinese company who made the hardware, at least the PCB, and you can see two chips, the NXP LPC microcontroller, which is used as a hub between the different communication interfaces and the secure element. And the secure element, it's also an NXP chip. And this device, this chip, stores the cryptographic keys and performs the cryptographic operations. We also found other FIDO products based on the same secure element. So the first YubiKey, it's a Swedish company which basically makes FIDO tokens. I think they are the first one, as they co-created the protocol. They were the first one to propose FIDO hardware tokens. And their first product, which is now discontinued, was a YubiKey Neo 1, and it was based on the same secure element. And also, FIDO, they also sell their products with their own brand. So you have these different models based on the same secure elements. And FIDO also, if you check on their website, they also can sell their products in a white label way. So that's how they subcontracted the development of the Google Titan key for Google. Now, when we decided to try to study the side channel security of the secure element of the product, when you dig in the FIDO protocol, there are some limitations for cryptanalysis attacks in the real world. First, there is no way in the FIDO protocol to extract your ECDSA private key. So, if, for instance, if I use my Titan key and I configure it to be used with my Google account, if I want in a legitimate way to extract my crypto private key to put it in another dongle, it's not possible. So yeah, impossibility to transfer the user credential from one token to another one. So it means that we will have to perform a black box side channel attack in an unknown key setup. So it's really hard because usually what we like to do in hardware attacks and cryptanalysis hardware attacks is to prototype an attack with the knowledge of the key. And once you are sure that you are able to recover the key that you know, then you can perform the attack on the field, kind of. It's similar to like, I don't know, like trying to hack the login page of the last Ubuntu version or Windows version. And it's easier when you know your password. You try to hack your password, and then you can sell your exploit to the NSA. But so what we did is like we said, okay, we need a chip similar to the NXP A700X, this secure element of the product. We need to find a product really similar to the secure elements, but where we would be able to load our own key to train ourselves. So we check the datasheet of the secure element, and we get for people knowing a bit the smart card world, we check that GCOP is the Java card operating system of NXP. So we get the version of the GCOP OS that was in the product, the technological node of the IC, the CPU, the different hardware coprocessors, hardware cryptographic coprocessors that were in the chip, and also like the version of the crypto library. Like the chip was able to perform RSA up to 2048 bits and ECC2. So this kind of information you can guess a bit. Okay, that this generation of the chip families and so on can help. And then we looked on the web a lot. That's what we do now when we are lost. So no, now we do ChatGPT, but at that time it was not released. And so NXP is famous to sell on internet some Java cards. And so we booked a lot of kind of all the Java cards we could buy from NXP. And so you have like all the models we found. So it's like 10, 20 euros the smart card. And we began to compare the datasheet. We also opened the packages to see the die of the integrated circuit of the chips, and to compare with the die of the Titan key. And when you know a bit the market of secure microcontrollers, you know that the first generation of NXP secure elements was the NXP P5 family or SmartMX. So P5 was the code name used by tech people. SmartMX was the marketing name. And this family of chips is quite famous in the smart card world because NXP sold billions and billions of these chips. So you used to find them in your biometric passports, in your banking cards, in your health cards, and so on. And this generation of chips, of course, were certified by Common Criteria and EMVCO. So Common Criteria, it's an international ISO norm for assessing the security of digital products. And EMVCO is the banking let's say industry that's the norm for certifying a banking product. But this generation of chips, the last certification they received was in 2015, because later NXP released a new generation of the P60 generation, and now they are at the P70 generation. So that time it was SmartMX1, then they released SmartMX2, and now SmartMX3. Anyway. So let's continue. And by comparing the data sheets and so on of the Java card we booked on internet and what we get as information from the secure element of the Titan key, we decided to choose this Java card, the G3B081 anyway, because it has the closest characteristics to the secure element of the Google Titan key. And Thomas, my associate, decided to call it Rhea, because Rhea is the second largest moon of Saturn after Titan. So now you can understand the title of the work, the side journey to Titan, because we have to first to stop in the first moon and so on. So we developed a custom Java card applet that we could load on this Java card, which allowed us to load a chosen ECDSA private key, to perform ECDSA signatures, and to perform ECDSA signature verifications. So we add our training device to try to reverse engineer the cryptographic implementation, and perhaps find a vulnerability, and perhaps perform an attack. So some words about the chips for the Titan. when you check on this picture, you can see that the chip is in an epoxy package. It's a black plastic, classical for microchips. So to expose the die, we had to go to the chemical lab to use fuming nitric acid that you put on the plastic to dig inside. And so we used some tricks of old guys of the field, like you put some aluminum tape around your product to protect it, and you cut a small window, and then you apply your acid, and you hope that everything goes well. And yeah, we succeeded to do something more or less clean, and at least the device still works after the chemical attack. And for the Java card, for the smart card, it's easy. You just have to use a scalpel and a bit of acetone if you want to seal a bit the transparent plastic layer. And here you can see the die of the chip. So with that, we were able to put the two devices under a side channel attack bench. The fun part is, like, at this step of the work, it was the first lockdown of the COVID. So we had to go to the office and to take some hardware parts to build. It was in my bedroom. It was during the first lockdown. And so here you have the smart card in the bench, and here is the Titan key, the chip of the Titan key, and you have the electromagnetic probe just put around above the chip. So about the side channel setup, it's like it costs about 10k euro. So the EM sensor, it's a longer ICR probe. For people who know side channel attacks, it's like the German company making electromagnetic sensors. It's really known in the field. A manual micromanipulator to be able to move precisely the EM probe above the chip. And as an oscilloscope, we use a picoscope, which is a USB scope without screen, but with really good characteristics from frequency, bandwidth, and sampling rate perspective. So finally we get our first electromagnetic activity traces of the ECDSA signature performed on Titan and on Rhea. And at this step, we could say, like, okay, the two implementations, at least the EM activity of the two implementations, look really similar. So probably that the Rhea, the smart card that we found where we can load our key, probably that's the same chip and the same version of the crypto library. So if we are right, we will be able to try to find a vulnerability on this product. And if we are able to exploit it, we could reproduce the attack on the Titan project. So then we began to perform really the main part, which is the reverse engineering via side channel measurements. So a few words about cryptography and ECDSA signature. So the idea of ECDSA signature, you have a long-term secret key and an input message that you want to sign. So what you have to do is, like, for every signature, you have to generate what we call a nonce. So this, if you perform 2 times the signature, this nonce should be different for each signature. Then you compute a scalar multiplication between this nonce and a public point of defined on the elliptic curve. And then you use one of the coordinates of the result of the previous operation, and you perform against some operations, blah, blah, blah. Anyway, the things, so yeah, in red, you can see that that's classical countermeasures that people implement when they implement elliptic curve cryptography for embedded systems. Anyway, I will come back in more details about that later. So just, we began to try to identify the different steps of the ECDSA signature. So at the beginning, there was kind of an init, probably perhaps generation of random numbers. So later we made the hypothesis that it was a way to encode the scalar and to project the base point. That's the first layer of countermeasure against additional attacks. Then the main operation, the most costly operation of the ECDSA signature is this scalar multiplication. We will see later what does it mean. And at the end, you have the other operation to finish the signature computations. We were not sure of the different steps. The only step we were sure was the scalar multiplication because it's really costly in time and it's like basically it's a loop of 256 operations of the same operation. So it's easy to find in the single. So here you can see that we were even able to separate the different iterations in a kind of precise way. And classically, you do this scalar multiplication with what we call the double and add always algorithm. So you will for every iteration you will double your input, and depending on the bit of the current bit of the scalar, which correspond to each iteration, you will add the input to the current buffer of the result, or to add it but discard the intermediate result in order to have something regular in time, to have like always the same operations and not to have something dependent on the bits of the secret. So we checked that there were exactly 128 iterations, but we are on 256 elliptic curves. So we were expecting 256 iterations. We are only half of the iterations. So when you check the literature about cryptographic implementations, probably this implementation uses the bits of the scalar 2 by 2. So that's a way to do that. Okay, so let's continue. We were like checking, you can see one iteration. So we saw that it was the first part of the iteration, the doubling, and then the addition with the initial message. Okay, so if we summarize what we get for the first reverse engineering of the ECDSA signature, we have a constant type algorithm, so probably a double and add always. We have 128 iterations for 256-bit nonce, so probably 2 bits are dealt by iteration. And we know that we are quite sure that the point is randomized via projective coordinates. Anyway, it's not really important for the rest of the presentation. So at that time, it was like, okay, we get some information on the implementation, but it's not easy to find a vulnerability. So we had the ID, which is a really old trick in the field, because the ECDSA signature uses the long-term secret key and the nonce. So it uses secret values. So when you are a developer of cryptographic implementations, you put all the effort on the operations using the secrets. But in this kind of crypto libraries, you also have the ECDSA verification command. So when you have a signature and you want just to validate that the signature is correct, and the ECDSA signature verification process doesn't require any secret. It only uses public data. So sometimes the developers, they don't put the same countermeasures on this public operation, let's say. So we decided to study this part, also this operation. So it's basic. When you check the algorithm, you have 2 scalar multiplications to perform for the ECDSA verification. So okay, it was easy to find them in the global EM activity of the operation. And as before, we were able to detect the different iterations in the signature process and the 2 sub operations of each iteration, the doubling and the addition. We could find the same patterns in the ECDSA verifications, but you can check here that double add, that it's no more regular. The scalar multiplication is no more regular. So it means that on the verification operation, it seems that NXP didn't apply the same level of countermeasures. So it's quite cool because with that, we are able to know that double add, so this is the one, double, we were able to read the key via what we call in section attack the simple power analysis attack. So we were able to get information of what are the values of the bits of the scalar, and with that we were able to. Okay, it's not constant time. The ECDSA verification. There is an expensive computation at the beginning. Okay, and we were able to try to reverse engineer the scalar multiplication algorithm because these two scalar multiplications are no more regular, as I just said. So we dig in the literature, and we found a really old paper from researchers from Toulouse, from the last, I think, and they propose a left-to-right comb method. So of WIS2. No, they propose what they call the comb method. So it's a way to perform a scalar multiplication, or you could also apply that to a modular exponentiation used for RSA. And so we said, okay, it matches with what we observe. Probably that is method. So what is the comb method? It's like that. You have your scalar, your nonce. Okay, you write it in the binary form. You cut it in 2 halves. 12 is, and then you write them like in a supervised way, and you take the bits 2 by 2, but like that, you know. So you take the first one with the first one, the second one with the second one, and so on and so on. And you pre-compute some points on your elliptic curve. Okay. So when it's a 0, 0. You add a point P0, which is a dummy value. We don't care because it's 0. So when you have 0, 1, you have you add the point P1 that you have pre-computed before your operation. 1, 0, P2, and 1, 1, P3. Okay. So now we understand a bit better how the implementation works. So now what we can do, we can associate a nonce bits pair to an electromagnetic subtrace corresponding to a scalar multiplication iteration. So it means that we can say, okay, here, sorry, we know that here it's a 1, it's like 0, 1, or here it's like 0, 0, and so on. So now what we want to exhibit a sensitive sectional leakage linked to the nonce bits pairs. So what we do, we take n ECDSA electromagnetic traces of signatures. Okay, so each trace has 128 iterations. For each trace, we cut it in 128 subtraces. Each subtrace corresponding to one iteration of the scalar multiplication. So we get 128 by n subtraces. And we can compute a side channel statistical test, like a SNR or a t-test, between each nonce bits pair and the EM subtraces that we created from recording the EM activity of several ECDSA signatures. And if we get, when we will compute this statistical test, if we get significant peaks in the resulting statistical traces, we know that we will exhibit a correlation between the data, so the nonce bit pairs, and the electromagnetic subtraces that we get. And if we're able to do that, we will have a way to, from the side channel traces, to guess the values of the secret. So we did that, and what we got is like in this part of the iteration, we got some peaks. So here it's a SNR, and we see several peaks in the. So this is some subtraces. This is the SNR statistical trace. We see some peaks. So it means that there are a dependency between the data and the side channel traces. And we also computed some t-tests on the most significant bit of the bits pair and the least significant bit of the bits pair. Why we did that? So here you have an illustration. If we superpose 1,000 subtraces, okay, the red ones correspond to subtraces where the LSB is a 0 the blue ones correspond to subtraces where the LSB of the bit pair is a 1. And you can see that it's not completely separated, but the blue ones are in this part, in this area, are a bit lower than the red ones. So even with Raman vision, we can see that in this small part of the long traces, okay, there is a dependency. The electromagnetic behavior of the chip leaks the data processed. So now, how do we exploit this side channel leakage? So we know that we can get information from the nonce-bit pair from the side channel traces, but to perform this side channel this statistical test, we use thousands and thousands of subtraces. And at the end, what we need to do is something in kind of one shot. So yeah, it's because in the ECDSA signature scheme, the nonce, this nonce which is used for the Scalar multiplication is randomly picked up for every new signature. So every time we play a new signature, it's a new nonce. So it doesn't work with the way we need thousands and thousands of subtraces to perform a statistical test and to make them working. So what we would like to do is to design a side channel process which matches with a high probability in one shot a single electromagnetic subtrace to a nonce bit pair value. With just one subtrace, it gives us it's a 00, 01, 10, 11. And for now, we need thousands of subtraces so we could go to the side channel tools that we call supervised tools, like in deep learning, when you learn, like template attack or deep learning, when you learn by having labeled data, and then you apply, you perform your inference phase on non-labeled data. Or we could use unsupervised side channel attacks tools, like clustering. So we decided to begin with the old school machine learning tools, clustering. And we succeeded with not a complicated process, but we had to take like this this trace is like hundreds of millions of samples. So we had to cut the part corresponding to the Scalar multiplication in 128 iterations. Then each iteration, as you can see here, it's like 2,000 samples. And at the end, what we want is like something really small to be able to perform clustering. And these kind of tools, they don't like too big data sets. So we were able to extract from the subtraces some point of interest, as we call it in side channel attacks. We use for that the statistical test that we perform to know, like for instance, this one. It allows us to this test shows us like when you take a subtrace, the statistical test tells you that at this abscissa, that's here that you get the most statistical information. So we were able to select the tiny samples that are useful for getting the information we are looking for. At the end, we were able, so we tried different ways. Of course, ideally, we would be able from one subtrace to match against the 4 cases, 0, 0, 0, 1, 1, 0, or 1, 1. But when we were considering 4 cases, the clustering was not working really well, and we had like, I don't remember, but perhaps 70% of success rate. So the idea of Thomas was to only concentrate on the LSB, because the LSB, even not the LSB, just the knowledge of like this subtrace, does it correspond to LSB equal to 0 or to something different? We don't even care if it's a 1 or not. And with that, we were able to do that with clustering was succeeding at 99%. So it's quite good. So at that time, we were able, from the subtraces, to identify the bits at 0 So if we write here the different nonces for each ECDSA signature, in average, we were able, so each nonce is 256 bits long, and in average, we were able to identify 27 bits at 0 by nonce. Okay, and so yeah. But now with the nonces, with parts of the nonces, we still don't have the long-term secret key. So then we had to use some tools that have been developed by mathematicians and cryptologists, like some people from the other team at ECDSA. And so yeah, when you have partial knowledge of the nonces in the literature, there is a mathematical problem called the HNP, hidden number problem, or the EHNP, it's an extension of the HNP, where the idea is like you have partial knowledge of the nonces in your ECDSA equation, and if you have if you can write an equation system with a lot of equations and the partial knowledge of some of the nonces, you can solve it if things goes well and go back to the long-term secret key. So that's the idea of the HNP algorithm. And the difference between HNP and EHNP is like HNP, you need to know the most significant bits of each of the nonces that you try to guess, and the EHNP is like some bits along, not necessarily consecutive, inside your nonce. And this extension of the problem is really less studied in the literature, so it was tricky to find some. You have no open source tool and so on, so you have to code yourself the stuff. So yeah, the techniques to solve these problems, it's based on lattice reductions. So lattice is a mathematical object that you will hear a lot in the next years, because the new public key cryptographic algorithms that will replace RSA and ECC, the post-quantum crypto algorithms, now are based on lattice lattice mathematical objects. So for that, you have some characteristics which dictate the size of the problem, which is the size of the lattice and the probability of success. So in practice, the EHNP problem, you need to know several consecutive bits. I said before, the EHNP, you can work on non-consecutive bits, but actually you need to know blocks of bits. If you have knowledge of only one bit alone and later another bit alone, it's not useful in this problem, in this mathematical problem. Anyway, we spent some time to understand that. We made some simulations to prototype our code and to better understand how this problem can be solved in practice with our constraints. And what we get is like with 80 signatures, with at least 5 consecutive non-nonce bits, we were able to solve the EHNP problem. So it means that we need, if I go back to this scheme, we need 80 nonces where we know at least one block of 5 consecutive bits. Yeah, but the problem is like we were, before I showed you that our clustering was working at 99%. So it means that in 1% of the cases, we get some errors. So here, what we have is like, you have the zeros that we guess. And like for instance, this one, it's not useful because there is no 5 zeros consecutive. Okay, and sometimes you have a cross because sometimes we made a mistake. The clustering makes a mistake. So we perform the pruning. So it's kind of brute force kind of, and from like 4,000 nonces, 4,000 signatures and so nonces that we guessed, we were able with that to get 180 nonces, more or less correct. And with that, we were able to finally perform the LLL prediction and to finish the attack on the Rhea, the training device in this with these characteristics. So we acquired 4,000 traces. So we were observing 4,000 ECDSA signatures. So that it took 4 hours of measurements. Then the processing of the traces, so cutting the traces in sub-traces, extracting the good point of interest, the clustering and so on, still 4 hours. And at the end, the LLL prediction and the brute force attack was like 20 minutes. So after all these different steps, we were able on the training device to retrieve the long-term secret key. So we said, okay, now we just have to apply the attack on the Titan product to be able to say, yeah, okay, we are able to perform the attack in the black box context that the Titan key provides. So for that, we reuse the same parameters for the side channel part, how to cut the traces in sub-traces and so on. And because actually the two chips, they were working at really slightly different frequencies, similar but a bit different. So we had to go a bit blindly to apply some, to replicate some parameters, but it works. We took a bit more signatures to be sure to have enough traces. And at the end, with 6,000 signatures, we were able at the end to retrieve the long-term secret key. And in this case, we require like 6 hours of measurements and after 6.5 hours of post-processing. So what does it mean is like, we were able to develop an attack to physically extract the ECDSA private key linked to an application secured by your FIDO device, your FIDO Titan key. But the attack has complicated requirements. The adversary has to have already stolen the victim's account login and password via a phishing attack. And then you have to have a physical access to the Google Titan key to the victim during, we say 10 hours because it's like 6 hours of measurements, but we consider that we need like 1-2 hours to get when we get the device to open the plastic case of the device, to perform the chemical attack, to expose the dye, put the device open under the side channel bench, then 6 hours of measurements. And at the end, if you want to perform the evil med attack, like we can see in some movies, you have to repackage the device in a really similar plastic case. So yeah, we try to be honest. We said we need 2 hours of preparation, 6 hours of measurements, and 2 hours for rebuilding like nothing happened the device and giving it back to the victim. And you have to have access to a chemical lab or a mean to see the package of the IC. You need a more or less expensive such an attack setup, and you need custom softwares. So it's not the click button attack, it's a bit complicated. So at the end, it's still safer to use your Google Titan security key than nothing. It's I don't think this attack will happen on the field. And so what we did is like we when we succeeded to perform the attack, we booked a lot of different products to check which ones are based on the same IC generation and the same crypto library. So we found a lot of different products where the ECDSA implementation is also vulnerable to attack. So it was a bit funny to constate that the attack can be like applied. It was not so funny for NXP people when we made the responsible disclosure, but it was an old product that they discontinued. So for them, it was not a big deal that we did that. And so finally, the NXP Security Incident Response Team confirmed that all the P5 and A7 products using the ECC CryptoLib up to this version were vulnerable. So some words about how to mitigate the attack. Something that is now in most secure ECC cryptographic implementation is to blind the Scalar. Is like the Scalar, the nonce. You can add a multiple of the order of the elliptic curve. Anyway, you can blind it. You can randomize it at every signature, and the result is still the same. The cryptographic result is correct. And by blinding the Scalar, it would have made our attack still possible, but we would probably have required like more and more traces to perform that. Another way would be to randomize the table lookup, which goes to get the different pre-computed points, because probably that is the addresses of the pre-computed points which leak. And in the FIDO protocol, you have also some optional protections that you can implement to detect clones. So you can, usually it's done on the server side in the FIDO protocol. On the server side, you can implement a counter. And so the counter will be implemented on the token and on the server. So every time you connect with your token to your Google account, for instance, if the counter protection is implemented, both programs will increment and will compare how much is the counter. Mine is this value. That's strange. We don't have the same value. Probably there is a clone with the same secret key linked to the same account. So yeah. But that up to the implementation on the server side. So usually that's not the kind of information that Google, Facebook, Dropbox, and so on provide. You just have to trust them. Google later said that they implement this protection. Of course, when we succeeded to perform this attack, we didn't try to do that online, because with some laws, when you try in the French law, when you try to connect illegally to a digital system, to a commercial digital system, you can get a trial for that. So we specified in our work that we did that. We did that. Everything was made offline, and in the French law, you have the right to test the security of your products, because you want to, if you want to be sure of that. So we were kind of careful when we decided to do the responsible disclosure to Google and to NXP, to not have any trouble about in the past. NXP used to make a trial to like a Dutch university who found the vulnerability like 20 years ago on the old MyFair smart card. So. And some words about the project timeline. So we got the first samples in end of 2018. We began to work a bit. Then during months and months, we didn't do nothing. And actually, it was thanks to the first COVID lockdown that we get more time. Like it was 2 months, I think, if I remember well. So at the first semester of 2020, we had plenty of time to work on that. And we validated the attack on Rhea at the end of June. And you can say that few days later, we were able to reapply the attack on the Google Titan key. And in October, we contacted Google, Phytian, NXP, and also the ANSI and the BSI for the coordinated responsible disclosure. And we said, okay, that's the work we did, and we plan to publish it in 3 months. So we let you some time to manage with your customers and so on. And we implied the ANSI, because ANSI is the authority in France about cybersecurity. And we try to be nice people, so we didn't want any trouble with the government. And plus, Thomas and myself used to work for the ANSI some years ago, so we know how it works. And the BSI, which is the French, the German ANSI, because the NXP chips, the P5 chips of NXP, used to be common criteria certified by the BSI some years ago. So it's normal in common criteria to contact the national scheme responsible in the country. NXP and Google were nice. They were not aggressive. They were okay, interesting, cool. Thank you for contacting us like that to be things properly. And in January, we published on the website and on the crypto ePrint the long version, the white paper of the work. And we assigned a CVE, and we published an academic version of the work at Usenix 2021. Sadly, it was in a full remote, so we didn't go to Canada that year. We were like in the office. It was not cool because it was like you had to make a video of 12 minutes, and it's really short. And so yeah, that's all for this work.